this session, I would like to demonstrate the calculation of Poisson distribution probabilities for a problem, and I will use the Python functions provided by the scipy library. So let's define a problem. So suppose that a person receives on the average, two calls per day. So this is an average value. Then develop a distribution of number of phone calls the person is expected to receive during a week. So develop a distribution of number of phone calls the person is expected to receive during a week. So this is a simple problem. So any number will be correct. But the difference in ordinary opinion and a scientific opinion is the calculation of probabilities. So let's define the variables. So in the code part, in the first cell, I have imported the essential libraries, NumPy for creating vector, matplotlib.pyplot as PLT for plotting, and scipy.stats as SPS, that is to call the Poisson distribution function. So the variable R is going to be discrete variable. So the person can receive from no call in that whole week to any number of call, any higher number of calls are possible. So let's define R for instance, that NumPy A range. So let's calculate probabilities for receiving say up to 20 calls from 0 to 20 in individual sense. We define a mu value, the mean value of the calls. So 2 calls per week. Actually, let's first write that one. The lambda value, since lambda is reserved, so I have used LAMDA, lambda. So 2 calls per day. So this is the number 2 for 2 calls per day. So now the time interval, T is a week, which means 7 days. So 1 week is 7 days. So now the mean value, so mu value will be 7 times 2. So lambda times T. This is the mean value. And now the probability density function, the calculation of individual probabilities. So I call it PR. So this can be calculated from the distribution function. Python is generous enough to create vectors for us instantly. So I would like to call this function. Yes, this is from scipy.stats.poisson. And I will look for the probability mass function. So it has 3 parameters, k, mu, and location. So probability mass function, this is the one which is required. So I call SPS, short for scipy.stats, as defined in this problem. So then Poisson. Then I am looking for probability mass function. So yes, PMF function, PMF. So the first variable is the discrete variable. the vector. So R vector was defined, R, and then I require the mu value and location. If not specified, it will be directly considered as 0, right? The distribution starts from 0. So let's see the results. Okay, there is no problem. We got the green signal from the computer that the calculations have been performed. And now our next task is to interpret the results. So I use a for loop for printing the values. I can directly print as well. So I write for I in range. So there are 20 values for R and therefore correspondingly 20 probabilities. So I write the print statement, print. So the first part will be with the format. So R values. Okay, let's write first the variables, the percentage, and I will print the values of R, Ri, and also I will print the corresponding probability values. So Ri values. So for every R value, there will be the probability, corresponding probability. So R values are integers, therefore I provide the format percent, say 4D, and then with the space, probabilities are going to be real numbers, therefore the format must contain the number of decimal places reserved for printing the fractional part. So I provide okay, up to 5 decimal places, and with F. F for floating point, D is for digits, and the end of loop is like this, right? So the statement, the loop will be executed 21 times. No, it will be executed for 20 times from 0 to uh, 19, from 0 to 19, and R was also from 0 to 19. So let's execute that one. Okay, so I got the bright right. Okay, I got the values. So getting 0 calls in 7 days, getting 1 call in 7 days. So you will find the uh, average number that was for 14. So we got this value, right? So it means the probabilities, further probabilities are to be calculated, right? So when you have the computer program, then you can extend up to any number, right? So 51, so that I have the good number from 0 to 50. So as this has been updated, I have to update all the calculations below. And now with these calculation, okay, it seems that the reasonable probabilities are up to well these numbers, right? So there is no need to go beyond 34, right? So they are very, very unlikely, right? They are very, very unlikely. So we have that estimate. And that can be established through the calculation of standard deviation. So now we have found that one. We have found the probabilities. If I apply the sum of probabilities, so that is the quick way to print one value. So it says the sum of probabilities is almost 1, right? If you want to calculate the probability for 100 calls, right, in a week, for a person who receives generally 2 calls a day, so for that person, it is even very, very unlikely to receive, but the computer can generate the number but that number would be insignificant. That's going to be something very, very rare kind of thing. So for Poisson distribution, the estimate of mean value can also be calculated. Uh, Mean value is calculated by lambda times t. We calculated that one. And if you want to calculate the standard deviation, so this is equal to the square root of mu value. The square root of mu value. And if I print this value, so okay, so the number is 3.74. 3.74. Our average value was around 14. So it means the majority of probabilities, roughly, they are within 2 standard deviations, right? Roughly, but you have to analyze the complete character. So let's see that one. If we consider that one, this number as, okay, the double of this one is going to be around 7. Let's consider 8, right? To be on safe side. So it seems that the majority of probabilities are 4 plus minus 8. So 4 minus 8, 14 minus 8 would be minus 8. 14 minus 8 would settle at 6, right? 14 minus 8, right? So you have this probability. And if you go 14 plus 8, that is 22. So you have this probability. But actually this plus, so you can consider plus minus 3 standard deviation to be on even more safer side, right? So that's how we generate the probabilities. And if you want to calculate the sum of only these probabilities, so you can specify, for example, this is possible like sum of probabilities around plus minus 3, um, around 3 standard deviations. So I can define the sum, numpy sum. So I can define probability of this one from the index 5 to say 26, right? From 5 to 26, the probability is is about 99%, right? So you can also calculate all other kind of probabilities. So the rest of the probabilities are even very small. They constitute even less than a 0.5 of the percent of probabilities. So this is about the Poisson distribution problem and probability generation. This belongs to a rare event probability characteristics of the systems.